Okay, so it seems to be 2 o'clock now, and welcome to the second lecture of this course, Introduction to Python. Before we begin, no, let's start with the slides. Yeah. So before we begin, I always ask if there was anything hard or impossible to do yesterday. So if there was anything you want me to go through, feel free to write it in the chat, and I will have a look at it, and I'll go through what that was. So just put it in the chat. And we can talk about it if you want to. I also have some practical information. So yesterday there was a question about the AC4 exercises and the PC4 exercises. So I've asked about those, and it seems like this week and next week you will be attending lectures, most of you, in Python. And then the week after that, so in about 2 weeks, you should that's when those exercises should take place. And I think the AC4 exercises, you will be given some information by Valentin Köhler, who will send this by email. And for the PC4 exercises, I think you should be receiving an email about that soon if you haven't already done that. Then I had a question about the graded exercises that you will be given on Wednesday. So there's been a few problems with setting up the system because there's so many students attending this course, and therefore we have to do automated grading. And apparently the system wasn't set up to have people from so many different courses. So that's something we've been working very hard to get running this week. And I'm going to be testing the system tonight. So hopefully tonight or tomorrow morning, I will send you out all the information on how to do hand in the graded exercises that you'll be given tomorrow. Yeah, is there more? Yeah. And also, I put up the lecture from yesterday. I can post a link in the chat here. It should be there. So that should be on YouTube now if you want to rewatch it or if you missed it somehow. Yeah, so let's go on. Apologize. So let's go on with what is going to happen today. So today we're going to talk about something called if and else statements. And so yesterday we basically just learned to calculate numbers and things. So today we're going to talk about how to make some more advanced programs that have like control of the flow through your for loops and stuff. So we will go through that, and also something called break and continue statements. So these are techniques to stop your for loops before they run to an end if that is a desired thing. And then lastly, we will talk about functions. And functions are basically a way to make code simpler and to reduce the risk of mistakes. And then we will beat this dead horse, the harmonic oscillator. So we will program that again using functions. And then finally, after that, so we won't spend so much time on the harmonic oscillator as we did yesterday. And after that, we will see how you can actually plot things in these Jupyter notebooks. And for that, we're going to use something called matplotlib, and we're going to use something called pyplot, which is a built-in library in this matplotlib, which is the standard Python plotting tool, basically. So one more thing. So for tomorrow, we're going to talk about numerics. So it's basically all the information you need for the next part of this course if you're taking the numerics intro. So for that, we're going to use a library called NumPy. So you've already seen it in some of the lectures when we say from NumPy or import NumPy SNP, and then we, for instance, use the exponential function from this. So this link here, I'll also post it in the chat. So that's a kind of a manual for NumPy. So I don't want you to like read every single line in the manual for NumPy, because that's I don't think anybody can remember all that stuff if you remembered it. But just like open it and look through it and like just get a feel for what capabilities NumPy actually has before tomorrow. And again, I posted the link to this in the chat. Another thing, if you haven't done so already, you can join this Slack channel that we sent up here. I posted the invitation link to the Slack channel in the chat as well. So join the Slack. And I also had a question yesterday. So let's exit these slides here. Like so. So I had a question yesterday, how do I open this Slack? So a person signed up but forgot how to sign in. So either you can go to this website here. Let me post another link in the chat. It's called Unibest Python Intro 2020.slack.com. So we can put that in here and see where it takes us. And yeah, so this is Slack. So it's kind of a message board that we can use to, like, somebody asked a question if I will upload the solutions and stuff, which I actually did. I will show you in a second. And I said, yes, of course I can upload it. And you can also send direct messages to me, or for the next part of the course, you can send to, I don't know if he's in the list. There should be Guido Falk von Rodolf here. Yeah, let's close this. Who's taking the next part of the course, or who's teaching the next part of the course. And you can, like, yeah, basically ask the teachers questions, or you can discuss, yeah, you can just discuss the lectures or exercises between you. Let's close this. So there is a question now about this. So I checked the solution for exercise 1, and I have a question. Why is the solution np.sign and not x equals np.sign np to grad? Okay. So may it be assumed that we always calculate in radians unless degrees are given? Yes. So NumPy always assumes radians and not degrees. That's just a convention. So you're absolutely right about that. Okay, so let's get started with the exercises for today. So let's go to Colab. Sorry, I have a Slack open. I'm just going to close it. So colab.research.google.com. So the same website as yesterday. And I'm just going to zoom in to make it a little easier for your people at home. And you can see yesterday, yeah, so we're going to go to GitHub, where I store all the lecture material and all the exercises. And then again, it was andersx, so it's Python intro, and I press enter, and it should find all the Jupyter notebooks that are in this path. I'll post these links in the chat as well here, and andersx/Python intro. So like so. So you see yesterday we had the intro exercises here, and we had the intro lecture here. And since yesterday I uploaded this file, so I cannot just, let me just show you quickly what that is. So here I just put in my solutions for yeah, for each of the questions. So if you want, you can check with your own solutions that you did the right thing. And yeah. And in addition to that, I also uploaded the intro exercises too. So the exercises after this lecture, and then I uploaded the lecture that we will, or the code that we'll go through during this lecture. So let's head into this file here. So I'm just going to click on it, and it should open. Okay, so this is open now. So one thing I found extremely helpful when I teach Python is to look at error messages. So before we really start with the lecture material for today, we're going to go through some debugging exercises. And these debugging exercises are really just, here I wrote 4 pieces of code, and they all have errors in them. And so we're going to run them and see what the errors are and see how we fix them. Yeah, so let's start with the first one here. The first one here. Error, I call it error 1. So let's press play here. And the first time you do it, when you get this from GitHub, you get a warning, but let's just run it anyway. And the first time you run something, it has to initialize everything. So yeah, and now it ran through, and you can see there is an error. And actually, you can see already the editor here, it like suggests that there's something wrong around here. You can see this red squiggly line. And so let's read the message here. So it says indentation error. U indent does not match any outer indentation level. So first of all, let me explain what indentation level is. So normally when we just write code, we write it all the way to the left. And as soon as we have something like a for loop, for example, we take everything that we want to have executed inside that for loop and we put it 2 spaces to the right, for example, here. And then once the for loop is done, Python assumes that everything should go back where it came from. So it should be in the same indentation level here as the for loop. As you can see, there's actually an error. There's an extra space here, which is also indicated by this squiggly line. And that's the error here. So it's the indentation levels that do not match. And again, if you're really curious, you could, or if you had no idea what this meant, because you had never seen this before, you could, for example, you could press this Stack Overflow button here, and you could, okay, in this case, it's not very helpful. But in that case, I would just copy and paste this message into Google and then see if I could find something that looks like that. So now that we removed the space, that probably was the culprit. Let's run it again. And yeah. It actually doesn't sum all numbers from 0 to 9. That's wrong. It just adds 1 for each number in this loop. Yeah, okay. So let's check error number 2. So in this example, I define a list. So it has 1, 2, 3, 4, 5 elements. And then I print the length of the list. And then I print the first, second, third, fourth, and fifth element. So let's see what happens when we run this code block here. And now it says index error, list index out of range. So what does this mean? Yesterday, we talked about how Python, it counts from 0. And then, so it's like 0. This is a set. The first is called 0, then 1, 2, 3, 4. That's how we index these elements in this list. And you can see I'm asking for 1, 2, 3, 4, 5. And 5 is obviously greater than 4. So what it probably meant was 0, 1, 2, 3, 4 here. Yep, so this is this error solved. If there's any question, just write in the chat. Otherwise, I'll just go through these one by one. Okay. So here again, I defined a list. So this is another list. It's called Y. And then I print Y. And then I print the entry in Y with the index 2. So I would be asking for 0, 1, 2. So we would expect it to print minus 2.5 here. And then it would print done. So print the list, minus 2.5, done. Okay, so let's see what happens here. Okay, so now we get a type error list object is not callable. So now what does that mean? So if you remember yesterday, we had so an example of a callable function, for instance, we had this np.exp. For instance, that if you want the exponential of a number, for instance, 1.0 here, let's delete this again. And let's not delete it actually. And you can see after the name of the function, I call the function arguments in these brackets here, or parentheses here. And you can see, so up here, I wrote Y, and then I wrote parentheses. And this actually means that you assume that this is a function. So this will actually be the focus, these functions of the rest of the lecture today. But the correct notation is not to use these soft brackets. It's actually using the, let me move the mouse so you can see, to use square brackets like this. So if I want the second or the index 2 element, I write Y and then square brackets 2, and that's it. So let's see if that works. Okay, so that seems to have solved it. And okay, so the last error here, so that's one I often make myself because I write sloppy code sometimes, but let's see what that does. And now it just says invalid syntax. So I write for I in range 10 here, and then I print I, and then I print done. So I would expect my code to print all the numbers from 0 to 9 and then print done. But instead it says invalid syntax. And the reason here is, if you remember, I'm going to show you one of the other for loops here. So every time you have a for loop, you end with a colon here. And you can see it's pointing, there's this arrow, it's pointing exactly where I made my error, or where Python thinks I made my error. So let's try to do this. Oh, and there's actually another error. So it says missing parenthesis in call to print. Did you mean print done? And you can see normally when I print something up here, I put it in parentheses, but here I forgot that. So we can just copy. I'm going to copy this. Whoops. And that was exactly what I suggested, and print done. And let's try and run this again here. Click. And now it's doing exactly what we talked about. Okay, so the reason I'm telling you all this, I know it's kind of boring to listen to, but it's incredibly helpful when you get errors, or to look at these error messages and figure out what they do. So no matter if you've been writing Python for 10 years or a week or a few days, you'll get these errors, and you'll have to learn to debug your code, and have to learn how to read these errors in order to debug your code. Okay, so let's go on today. So with the next point. So we're going to talk about something called if and else statements. So all the codes that we've been looking at have just executed something sequentially. So just do one thing after another, completely sort of deterministic. Now you can also set up conditions such that the code will only be executed if a certain condition is met. And to do that, you use, for instance, you can use this if statement here. And just to demonstrate, I have put one of the most basic examples I could find. So I have two numbers, A 33 and B 200. And I say if B is larger than A, colon, and then an indentation. So everything that is in this indentation kind of belongs to this if statement. So you can see what I'm writing here is if B is larger than A, print, or B is greater than A. So let's see what happens here. Great. So it means this bit gets executed because it's larger than A. We could try and reverse this. So if B is smaller than A, which it is not, then actually nothing happens because we didn't define anything to happen in that case. So you can do it a little bit more advanced than this. So we can call this branching. So here we have another example. So we have A 33 and B is 20 here. And now we say if B is larger than A, print B is greater than A. And then we have this else colon. And remember, this else it has the same indentation level as the if and the outer indentation level. And here we can say, so for instance, print B is not greater than A. So let's see what happens here. So now you can see first we check if B is larger than or greater than A, and B is 20. So this is not the case. So it doesn't execute what is here, but then instead it executes what is here. So this is pretty simple, and you can make it even more advanced by using this. It's called elif. It's short for else and if, like contracted. So it's the same example again. So I could say if B is greater than A, print B is greater than A, and elif B is equal to A, then print B is equal to A, and then I could say else B is smaller than A. In principle, I could put as many elif statements here as I could think of. I can't think of any good thing to put in here right now, but you could expand this with as many elif statements as you would wish. So here in these examples, I just use this if B is greater than A, or if B is equal to A. So there's a lot of these checks you can do. And here I'm just writing some of the most common. So if you want to check if two things are equal to each other, you use this notation, two equal signs. So we can, for instance, see if you mouse over a variable in these Jupyter notebooks in Google Colab, it will actually tell you the value of that variable currently. So we can see B is 20 and A is 33. So obviously this should not be the case. So we can try and run this, and it would actually tell us that this is false. So we can try and say, is A, which is 33, is that greater or equal to, which is this greater or equal to sign just right after each other. So let's try and run this. And of course, that is the case, so it returns true. And the same way we can do, if A is greater than B, true. Is A smaller than or equal to? It's not, so it returns false. And again, we can try A is smaller than B, which is not, so we get false. And then finally, this one means A not equal to B. So let's try and run that. And of course, 33 is not equal to 20, so we get true here. So these values, true and false, they're actually a separate type. And these are called, whoops, I was too fast here. These are called Booleans, and like tests like this, and this is actually called Boolean algebra. So you can Google this term if you want to read more about all this. And you can actually make a variable and set that to true, for example, or you could set it to false. And then we can, just like any other variable, be it a number or a string or something, we can print it. And then we can also print the type just like we did yesterday with floats and integers and strings. So let's see what happens when we run this. So we set myvar to true, and this is always with a capital T, by the way, and if it's false, it's a capital F. So it prints myvar, and then it prints type of myvar, and we can see that it says that the class of this is bool, so like shorthand for Boolean here. Whoops, like that. So you can see, for instance, in this case, A is not equal to B. That is true. So we can also use this true here. So we can say if myvar, so if something that we just set to true is true, then this will happen. So we can try and run this, and this was also, this will be true. So for example, if we let's uncomment this and set my underscore var to false. Let's see what happens here. So if we try to say if something that is false, then it doesn't do it. Yeah, and you can actually combine statements like these, and you do that using some keywords called and, or, and not. So for example, if we want something to happen, but we only want it to happen if two conditions are met, for example, like this. So we only want it to print complicated if A is larger than B and A is equal to 33. And you can see we set A to 33 here and B to 20 here. Then it prints complicated, and you can expand it even further. So this is an example of the and. So let's come up with something where we can use the or. So we can actually put additional parentheses around these, and then we can say or, for instance, B equals, I don't know, 15 or 12 or something. So if either B is 12 or all these conditions are met, this will happen. Yeah. And you can see I actually just made a bug because I was supposed to put double equal. Yeah, exactly. Here. Yes, exactly. So in the exercise today, I think there are 2 exercises where you'll use these. So hopefully you can go back to this lecture material, and you can see how to use them later. There are also some instructions in the actual exercises. Okay, so let's go on to the next point of the day. So this is called break and continue statements. And these are really things, so normally when we write a for loop like this, so we want this for loop to run for I in range 100, so we want this to run 100 times. But sometimes you want to stop your loop before time for whatever reason. So let's say here we only want to print up to I equals 5. So we can, for instance, say for I in range 100, and if I is larger than 5, so basically we want number 5, but we don't want number 6, and so on. So we can say if I is larger than 5, then break. And break means stop the for loop entirely and then continue with whatever was down here. So if we print, for instance, print ended here. So let's see what happens when we run this code. 0, so instead of printing all the numbers, when it came to number 6, so the first time it checks, so for 0, it checks, is 0 larger than 5? No, so it prints 0, blah, 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 up to 6. Is 6 larger than 5? Yes, it is, so it breaks. So it skips everything else that is inside the for loop, and it jumps down to the next line after the for loop to that indentation level here. And we put in this sign called ended, so it printed ended here. Okay, similarly to this, there is also another thing which is not used as much, but it's called continue. And what continue does is that in contrast to break, where you break the entire for loop, continue only skips everything else in the current loop. So one example I could come up with where we use this is, for instance, if we want to print all the odd numbers. So we can use, again, just a simple for loop for I in range 20. I'm using this notation here. So if you don't know what this means, so this is a modulus operator. So for instance, maybe I should, here we can, so the modulus operator takes a number and divides it by another number. For instance, let's say 5 modulus 2 here, and let's run that. Yeah, so what this does is it sees how many times you can divide 5 by 2, and that's 4 times. And if you do that, there's one remainder. So the answer is 1. For instance, if we put 3 here, you can divide it 1 time, and then there are 2 remaining. So it gives 2. So if I take any number, so 17, for instance, so that's an odd number. It will, and you divide it, take the modulus 2, it will always return 1 because it's an odd number. So this should return 1. And similarly, if you put any even number, it should return 0 here. Okay, so let's close this for a second. So let's print all the odd numbers. So what I'm doing here, I'm checking if I modulus 2 is equal to 0. So if this basically says if I is an even number, then I continue. And continue means just jump back up here. So if this condition is not met, so this will only happen for odd numbers. So if this doesn't happen, this will only happen for even numbers. So if it's an odd number, it will continue down here, and then it will print I here. So let's see what happens. And you can see as we wanted it to, it prints 1, 3, 5, 7, 9, blah blah blah, all the odd numbers. Okay. Any questions so far? Just fire away in the chat. I don't think so. Okay, so let's go on to the meat of the day. So let's talk about what functions are in Python and how to write them. So if you remembered yesterday, from NumPy, we imported this function to do the exponential. And let's just run that code so we remember what it does. And functions, they work like this. You have the name of the function, and then in parentheses, you write the arguments to that function. Yeah, and for instance, this exponential function is defined inside this NumPy library here. So what if we wanted to write our own functions? How do we do that? So one example I have here is one of the simplest functions. It's a function called f of x, and it just returns the square of x, basically, here. So here I wrote how you could define this. So there are many ways to do this, but this is definitely one of the most straightforward. So if you want to define a function, the first thing you do is you write this keyword def and then space. Whoops, sorry, I moved it. And then you write a name of the function, and it's a good thing to have a descriptive name for your function. So for instance, this calculates the square of your x. So let's just call this square. And then here as arguments, yeah, just like this function, the mathematical function takes x as an argument. We can put x in here. Then inside the function, you carry out the calculation that you want to do. So in here, in this case, we want to calculate f, which is equal to x squared. So I just write x equals to x squared. And then finally, we have this new statement that you haven't seen before. So it's called return, the return statement. And it's what you want to come out, what you want to have come out of your calculation. And in the end, what you want to have come out of your calculation here is the value of f, which you calculated on this line. Okay, so let's try and define this. So let's just run this cell block here. And let's try our new function. So print, for instance, the square of 2. So let's see if this gives 4, as it probably should, and it does. Okay. Okay, so this is not terribly more easy than just writing x squared. So this is more a thing you would do with some more complicated functions. So here, I'm just going to show you and demonstrate how I would write a function that is more complicated. Okay, so yeah, here we have another function, and we can take a look at it. It does a summation, and then it takes x to the power of n, and it does a summation over n. So this looks like something that we calculated yesterday. Okay, so let's start by writing this function. So the first thing we write when we do these functions is def. And then we have to come up with a name for this. So one name could be power sum. Could be a good name for this because it has something to do with like taking x to the power of n, and then you sum over it. So maybe power sum is a good name. But you can give it basically any name you choose. And then in the parentheses here, you have to write what it takes as an argument. And in this case, it takes x as an argument. And just like when you end the lines with for loops or if statements, you end the line with a colon here. Okay. And Jupyter Notebook actually automatically like indents the code after you write a colon, so it makes it less likely that you'll fuck up your indentation level. Okay, so let's implement this and see what it does. So it's a sum over n from 0 to 10. So we could write, for instance, for I. Actually, let's write for n, because here we use n as a variable. So for n in range, and since we're going up to 10, Python only stops us one less. So let's write 11 here, and then just a colon, just like we did yesterday. And you can see Python automatically jumps in here. So what should we do there? We should, for instance, we could call it f equals 0, just to start the value of f inside our function. And then we can say f equals f plus an x to the power of n here. Okay, sorry, like that. So now we implemented this loop here. And then the last thing that we always need inside a function is a return statement. So let's write return here. And what do we want to return? We want to return f, which was the variable that we summed up in. So let's see what happens when we run this. So at least it accepts our definition. So let's see if we can use this function. So let's print power sum of, let's say 3. Let's see what happens. So it gives us a number. Now I don't have anywhere to check if that's the case, but this is definitely how you would write a function. So if you don't have access to IPython Notebook right now, I also I put a solution down here. I think it's actually exactly the same code I wrote up here. It's in this hidden cell block. Okay, so a very common error with defining functions is something I put here. So just like the function we had before, called squared, this is called cubed, and what it does, it takes x cubed and calculates that. And then down here, I print cubed of 3, so 3 to the power of 3, so that should be 27 or something. And now you can see, if I run that, it says none. So what the hell is going on here? I just told you that you always need this return statement because this is what comes out of your function. Okay, and here is a return statement. Nope, there's not. And none is the Pythonic way of saying nothing, basically. So nothing comes out of this function is what Python is saying, which is actually legal, but usually not what you want. So for instance, we can put in here return, and we want f to come out of this. Here, let's see if it prints 27, and it does. Okay, so basically the point of all these functions is that, let's say you had to use this function here many, many times. You wouldn't want to ever write this entire loop. Let's say you had to use it 100 different times. You wouldn't want to rewrite all this 100 times. What you want to do is just call it with a function every single time that you have to do this. So you can see this code here is much more easy to read than if you had this code in like a long Jupyter notebook or something, right? So this is the point with functions. So it reduces your chance of writing bugs. So if you had to implement this multiple times, you would probably one time you might like skip something like that, and then you would get a bug somewhere that would be extremely hard to find. Whereas if you implemented it once and called it this way, you know that if it's correctly implemented in one place, you'll get the correct answer every time. And if suddenly there was a bug in your code, you know very easily, because then every time you called it, you would get the wrong answer out of it. Okay, so let's go on with. So I'm gonna use the same thing as we looked at yesterday. So the heat capacity of this harmonic oscillator, and today we're gonna calculate the heat capacity as a function of the temperature, and we're gonna plot that. Yeah, so we're gonna rewrite the code a bit for today, and then we're gonna end up with some plotting at the end of this lecture. So yesterday we went through all the theory here. So we have this Morse potential for this diatomic molecule. So if you compress the molecule, the energy goes up, and if you like dissociate the two atoms, the energy goes towards the dissociation energy, and you have these vibrational levels here. And we have all the equations for the energy and the probability of observing a given state, and we have the partition function, the internal energy, and so on. And we also went through the heat capacity, so the change of internal energy with respect to a change in the temperature, and how that was calculated. And it was calculated using the internal energy here, so this expectation value, and the second moment of the energy also here, which we calculated this time, like this. And if you remember at the very end of my last, the lecture from yesterday, I had some extra code that I invited everybody to look at. And here is that exact code. So this is the code to calculate the heat capacity as a function of the temperature. And so I wrote this code, and when I look at it, I think, what the hell is that? It's completely unreadable at first glance. So yeah, I would like to end up with some code that looks way better than this, because it's hard to find errors when things are implemented like this. So I hope I can now show you using functions that you can actually implement this code in a way better manner. So let's hide this guy here. Okay, so yesterday we had this example 1 where we printed the energy epsilon n for each state up to n equals 3. And I wrote the code here, and we just implemented it like a for loop, and we wrote epsilon equals n plus a half. Now you could easily write this calculation here as a function, And for instance, you could call it epsilon. So you would say def epsilon n. And then inside the function, you would write the exact same as up here. So for instance, e equals n plus 1/2, and then you would return e. So for example, for the first, for the excited state with n equals 1, the energy would be 1 plus 1/2. And let's see if that comes out here. Yeah. And this means that every time, instead of implementing this calculation here, we can now just implement a call to this function called epsilon. So hopefully I will show you how that will simplify our code today. Okay, so let's look at the partition function here. So there are several things that I want to change from the code yesterday. So this is the code we had yesterday to calculate the partition function. So we have the temperature. Whoops, sorry about that. We have the temperature, and we had the partition function that we initialized to 0, and then we did this. Remember, we had this loop that went all the way up to 10,000 just to get the sufficient accuracy of the value of z, and then we had this ugly loop here. So now we could try and instead, every time we need the partition sum, we would have to write this loop. That's what we did yesterday. But instead, let's try and write it as a function this time. Okay, let's do this here. So the first thing we do, because we need the exponential function, is to import from NumPy, import NP. And once we've done that, we can actually start writing the definition of our function. So I just write def, and then I have to give some kind of name, and it can be any name you like. So I think partition would be a descriptive name for this. And if let's look at the code again here. So I wrote it more explicitly than I did yesterday. I wrote that it's a function of tau, right? So the only thing that this depends on is tau. Yeah, so that's why we can put tau in here. And then we actually do the same loop as yesterday. So we start to see with 0, and then we can, instead of going to infinity, we can go up to maybe 10,000. And then if you look what we wrote yesterday, we wrote z equals z plus np.exp. And then here we had the explicit calculation for epsilon, so n plus 1/2 divided by tau. So instead of this, I don't want to write this many times. I only want to write this and implement this in one place. So if I implement this more times, I might somewhere I might write n minus 1/2 or something, and it would be extremely hard to debug my code. So instead of doing that, I'd rather use a function call to my function that we defined previously, the one called epsilon. So now you can see z equals z plus exponential. Maybe I can, yeah. Now you can see this at the same time. So z equals z plus the exponential of epsilon of n divided by tau. And so this looks way more like what we had up here. So I would say this is a better code for this problem. And we can see now, let's have the partition function for a particular value of tau, for instance, 2.0. What we can do is simply, when the partition function is defined, we can just make a function call to that function with the right argument, and we can, for example, store it in a variable called z2, and then we can print that. And now you can see it's saying namer partition is not defined, and that's actually because I didn't run this code block. So if you have a function definition, you have to define the code block, and to get that done, you have to run the code block. So if I press play here, it should work now. So let's see what happens. And this is the exact same value as we got yesterday, so we can feel fairly confident that this is correctly implemented. Now, if you remember yesterday, we tried to change this number here. So let's translate it to 100 and run again. Let's run this again after we set that to 100. And you can see you get the same number again. So the question is, the question I've written here is when should we stop the loop? So instead of trying 100, 1000, 10,000, whatever. Is there any way that we can stop the loop in a more sane way? And as we talked about previously, we can stop loops using this break function here. So when should we break the function? So let's say that we want, for example, we want the partition function to 5 decimals. So that means if the thing that we add to the partition function every loop, if that becomes lower than 0.000001, then there's actually no need to continue with the loop because that's lower than our threshold. Okay, so let's see how we can implement that. So first, let's just set this to maybe 10,000. So let's, we can call this the contribution. Actually, let's call it, this is called the Boltzmann factor. So we can call it Boltzmann factor. And that is equal to, I'm just going to copy and paste it up here. And then we can say if Boltzmann factor is less than 0.0001, for example, then we can say break to stop the code there. And then let's say we don't want to calculate this multiple times. We could just add this number here. So let's see if this works here. So let's see if we get something similar. And you can see the first couple of numbers changed, but the last ones didn't. And we can, in principle, increase the tolerance a bit. So there's another way of writing exponential. So 10 to the minus 5, you can write it like 1e minus 5. So that should be what we just had. So let's try that. That was just, so let's try 1 to the minus 8th. And now we should get a more accurate calculation. And yeah, the first digits didn't change again. So this is one way we could have avoided what we had yesterday, where we had to like do trial and error to find out what the correct number to put in here. So let's see how many iterations we actually do. So we run this loop for up to 10,000. So we can print, if I can spell it, we can print n. So that's the iteration of the loop. And then we can print Boltzmann factor. So let's put there, and let's see how many loop iterations we actually get in this. So it seems like if we want 10 to the minus 8th accuracy, we can stop after this 36th iteration. So now you can see this function to calculate the partition function, it became longer and longer and longer. And if I needed the partition function in more than one place, I would not want to write this code again here anywhere else. So it's much easier for me now to just call partition function of 2.0. So I hope that makes sense to you. I'm just going to remove this output here. So when do we stop the input, or when do we stop the loop? Can we use breaks? So that's what we just went through. Okay, so example 3 here. So again, it's what is the internal energy U for our system for tau equals 2.0. And let's, for instance, look at the expectation value here, which is the energy of each state multiplied by the probability of each state. So this is sum over all n up to infinite here. Yeah, so let's try and break it down. What do we need to calculate this? Well, we basically need a function for the probability. Oops, sorry about that. And I've written the function for the probability in more detail here of a given state, and you can see it's the probability of a given state at a given temperature. It basically takes 2 input variables. So in the examples we had before, we only had one input variables, but you can have actually as many as you like. So you would say, in this case, for the probability, we can call it prop is probably a good name. So call it def prop, and let's see what it has arguments. So it has n and the temperature tau. So we put that in parentheses and colon. So now what do we need to implement this? So first of all, we need you can see we need the partition function. And we already defined that up here. So we can get the partition function just by, say, partition tau here. So that's what I do on this line. It's just one function call. And then I can actually calculate the probability P just by calculating the Boltzmann factor like I did before and divide it by the partition function. And if I call that P, I can return P. And so let's just test this and see if we intuitively can see if we're right. So we know that the lowest lying energy level has the highest probability. So if we print it for 0, it should be larger than 1, and which should be larger than 4. And if we print it for the 100th, n equals 100th state, it should be a very small number. So let's see if these probability numbers work. Oh, yeah, this is a bit bad. I forgot to remove this print statement here. So I'm just gonna rerun this with this print statement removed. And let's try and run this cell here. So now you can see it's printing the probability of the 0th state, and that's 39% roughly. And the first has 23%, and then the 4th has about 5%. And then the 100th state, which we hope or which we thought to be very insignificant, it has only, what is this, 8 times 10 to the minus 23rd probability, which is completely what we expected. So now we hope that the probability is also properly implemented. So let's actually go on and implement these here. So for instance, the internal energy, which is the first of these, so it's this expectation value, a good name for a function like that would be internal energy. And the internal energy would only depend on the temperature. And here I'm a bit sloppy. I don't want to do the whole break thing again because that's going to make the code too messy to look at right now. So I'm just going to sum up to the range of 100, so only up to the 100th state. But you can see we're doing the exact same thing as we did yesterday. So we took the U, and then every state yeah, there's not enough. Maybe if I zoom out a little bit, maybe there is. Yeah, so you can see it's a sum over every n, and it's a sum over epsilon, which we implemented, and multiplied by the probability for n and tau, which we also implemented here. I'm going to zoom in again. Okay, and for the second moment of energy, it's the exact same function. The only difference is there is this extra square here. So with these two implemented, let's try and run this. And the output here will be the internal energy at 2.0 and the second moment of the energy at 2.0. Yeah. Okay, so finally, we wanted the heat capacity as a function of tau. Here. So basically, we want a function of the heat capacity that's called the heat capacity, and we want it as a function of tau. So for instance, yeah, so what does it require? It requires to calculate the second moment of the energy and the internal energy squared, and then divided by tau 0 or tau squared. And we just implemented these two as separate functions. So we can just calculate, for instance, we can call U, which is the internal energy, as a function of tau, and then the other function we just implemented, which was called second moment, also a function of tau, and we store those in variables. And then we can actually calculate this ratio here. So U2 minus U squared divided by tau squared. So we store that in this variable called CV, and then return CV. And let's try and print the heat capacity at 2.0, for example. And it's just below 1 in the units that it's in here. So this seems to work. Okay, so the thing that we actually wanted to do, that we set out to do, was to print CV or calculate CV as a function of tau. So just like we did with the for loops and list yesterday, so here I defined just some temperatures that I thought might be interesting to calculate the heat capacity for. And then I just say for tau and temperatures, CV equals heat capacity, and heat capacity was this function we defined up here as a function of tau, and then it prints tau and CV. Yeah, and that's apparently what those are. So I hope I can convince you that this way of writing the code is much easier to do than where was it? Up here. So this is the ugly code from last time. Like this code does exactly the same thing. It prints for the exact same tau values or temperatures. It prints tau and the heat capacity, but this is very difficult to look at and to debug if you were to do it. Whereas if you have the new code that we wrote, where is it? Where did it go? It's up here. This would be easy to find bugs in because everything is packed into separate functions, right? Okay, so one thing that is very normal to do when you print or when you calculate something as a function of something else, that has to do with plotting. Let me just remove this. So if we want to plot actually the heat capacity as a function of the temperature, first of all, we have to save the heat capacities that we calculated somewhere, and preferably we could, for instance, use a new list. So if I wanted to calculate the heat capacity for all these temperatures here, let's say I wanted to save them in this other list called heat capacities. So this is plural, and it does not have the same name as this function, just to be clear. If it had the same name, you could no longer call the function. So if you want an empty list, and then my idea is I would calculate the heat capacity for a temperature, and then I would add it to the list. So when I've calculated for all the temperatures, I've added the heat capacity for every corresponding temperature to that list. Okay, so we start by initializing an empty list here, and then we say for tau and temperatures. So for each of these temperatures up here, we do this loop. And what do we do in the loop? Just like we did in the previous example, we calculate the heat capacity for that tau and store it in the CV. And then something new happens here. So we take this empty list called heat capacities, and then I use this function called append. And append means add to the end of that list. And to the end of that list, I add this thing called CV here. So basically, this loop says calculate heat capacity, put it in this list called heat capacity, which starts out empty, but then it gets filled up on the way. And finally, I print the heat capacities here. So let's try and run that. Okay, so we have a technical error here. Let's remove that. Yeah, sorry, that was a brain fart from me. Sorry about that. So the problem was that the partition function, or the tau here, was so small that yeah, that when you divide by it squared, it becomes undefined. But anyways, so what we have here is for a list of temperatures, we calculate the heat capacities, and then we add to this list the heat capacities, and then finally we can print the heat capacities here. So apparently these are the heat capacities as a function for all these taus here. Okay, so how do we plot these in Jupyter notebooks? And actually, there are some built-in tools for this. So right here, to plot a graph, we can use something called pyplot from matplotlib. And the way it works is just like the NumPy stuff we imported. You just say import matplotlib.pyplot, and the convention is to import it as PLT. So every function from pyplot and matplotlib, you will use PLT to access. So just like we access all NumPy functions by using np dot something, all pyplot functions are called PLT dot something. And now let's construct the plot. And if you want a line plot, so that's what you normally plot functions as, the command is called plt.plot. And then the first argument is your x coordinates, and the next argument is your y coordinates. So we want the heat capacities as a function of temperature, so we would write them in this way. So and then once it has constructed the plot, there's a command to actually show the plot in the Jupyter notebook. So let's try and run this code here. And then, well, it actually draws a plot directly in the Python notebook. So this is extremely helpful that you can actually see. So if we, so that you can actually see like right away what things look like. You don't have to compile anything. And one thing about these matplotlib galleries, or matplotlib and pyplot figures, they're extremely easy to customize. So you can change the color or the plotting style or whatever. I recommend that you, if you want to look further into this, I've put a link here to the matplotlib gallery. I'm just going to show you what it looks like for a second. So let's click this link. I'm going to zoom in quite a bit here. So what this gallery has is basically a plot of every type that you can imagine. So bar plot, heat maps, everything, scatter plots, correlation plots, everything is in here. There's so many ways to customize these. And if you want to see the code for something, you can just click on that particular plot to get the code for that. And then you can make your own plot that looks somewhat like that plot. So this is an extremely helpful resource if you do use Python for anything and you want to like visually visualize the results. So I'm just going to show you some of the customization things that you can do. For instance, you can, I wrote some things here, and let's just go through what they do. So the first one, you can say plot figure, and then there's this argument called fixed size. And this adjusts the figure size in inches. So let's have an 8x8 figure instead of, I don't know what the ratio is here, but it's definitely not square-ish. Then another thing that is helpful to do is, for instance, add labels to the axis. For instance, our figure, we might want to call the x-axis tau, and then the y label would be heat capacity. So it would say tau here and heat capacity here. And then also a title to your plot. So we could write quantum harmonic oscillator here. And then, for instance, we can display grid here. Yeah, and then finally, once you have set all these things, we can plot it here. And we show it just like we did before. Here, so let's see what happened. So now we got a much bigger plot, and you can see the labels and the titles are exactly what we did, and it's displaying this grid, so it's easier to. It might be easier to read whatever is in this on this graph here. So this was basically all I have planned for the lecture for today. So let's maybe I should introduce the exercises. So let's go to let's open Notebook and go to GitHub here. So first of all, I want to say I uploaded the intro exercises 1 to solutions here. So these are basically, I think I actually did that. I told you about that in the beginning of the lecture. So the new thing today is the intro exercises 2 2020. So these are the exercises for tomorrow. Whoops, sorry, I screwed that up. GitHub. So let's open these intro exercises 2. So in these exercises, you'll basically go through everything that we learned today. So you'll learn to define a function, and you'll try to define your own function. And there's like an exercise with a loop and a function that you'll do. And then there's some things you can implement with these if and else statements. And then there are some exercises by the end of it where you learn to do plotting of not just line plots, but you have to plot scatter plots. And tomorrow there will be some other plotting exercises. Yeah. So this is basically all I had planned for today. So let me know if you have any questions at this point. Yeah, so just put your questions in the chat if you have anything